Hello and welcome to lecture 57 of analog integrated circuit design. We will continue our discussion on continuous time filters. We will start from second order filter prototypes and see how to realize them with op amps and transconductors. Now, it is assumed that we already have a prototype passive second order filter and we start from there and synthesize the active counterpart. Now, the business of finding what transfer function is optimal, what order we should use and the prototypes and so on can be found out from either simulators like MATLAB or from sources like the book by Zverev. Okay. Our only job is to translate the passive prototype into the active one, and which can be generally done for any filter of any order. Okay. So, we will consider second order low pass filters, and a second order low pass filter prototype can consist of many forms which are sort of related. This is what is known as doubly terminated, because there is a termination resistance at the input and a termination resistance at the output, and you can also have it only on one side. Like this is an example of a singly terminated filter. Let me label these L1 and C2, L1 and C2, and this is an example of also a singly terminated filter. In this case, the resistance is on the output side and in this case on the input side, and these are driven by the input voltage Vi, and in the doubly terminated case I will make the input signal 2 times Vi. This is just to take into account the attenuation at DC. We have R and R, so the DC gain will be half when the inductor is a short and a capacitor is open. So, just to make all of them the same in terms of their output voltages V0, I will apply 2 Vi. Okay. Now, the transfer functions V0 by Vi can be easily derived for all of them. I am not going to do it here, but they turn out to be in this case, and we will have 1 by S square L1 C2 plus S L1 by R plus 1 in this case, and similarly 1 by S square L1 C2 plus S C2 R plus 1. Okay. Now, the natural frequency of all these filters is the same, and that is 1 over square root of L1 C2. It is the same for all of them. A second order system is characterized by its natural frequency omega p and the quality factor QP. Okay. And in this case, the quality factor is 1 by R square root C2 by L1 plus 1 over R square root L1 by C2. Okay. And in this case, it will be R square root C2 by L1 and in this case it is 1 over R square root L1 by C2. Okay. So, these are just 3 second order low pass filter prototypes, and we will see how to turn these into active forms. Okay. The components that result in filtering are the inductor and the capacitor, and we have to synthesize the function of these things in some way without actually using inductors. That is the idea, because on chip inductors cannot be made of very large value, they occupy a very large area. So, we will stick to using active elements and capacitors. Okay. If we manage to realize the node equations describing these circuits using only active elements and capacitors, we will implement the same function. Okay. For that, we will first have to write down the node equations of these. Now, the node equations are written in terms of the state variables. There are two state variables in each case, the inductor current I1 and the capacitor current V2, and the output voltage is equal to the capacitor voltage in this particular filter. So, I have I1 and V2, and similarly I1 and call this V2. Okay. So, what I will do is relate the voltage across the inductor to its current. Okay. That is the equation describing one of the state variables, and we have one for another state variable. In general, if you have an nth order filter, you will have n such equations. So, first of all, the voltage across this inductor L1 will be equal to SL1, the impedance of the inductor, times the current I1. Okay. And what is the voltage across this? It is this voltage minus the drop across the resistor. Okay. 2 Vi minus I1R, that is the voltage at this point, and the voltage on the other side is by definition V2. Okay. And this will be equal to SL1 times I1. Similarly, the current through the capacitor C2 will be the voltage across the capacitor times S times C2, which is the admittance of the capacitor. Okay. And what is the current flowing through the capacitor? It is I1 minus the current flowing through this resistor, which is V2 by R. Okay. And similarly, I will write it for this, the voltage across the inductor is Vi minus V2, and that will be equal to SL1 times I1, and the current through the inductor is I1 minus V2 by R, and that will be equal to SC2 V2. And for the last one, the voltage across the inductor is V1 minus I1R minus V2, that will be equal to SL1 times I1, and the current through the capacitor is nothing but I1 itself. Okay. So, essentially we see that a certain set of electrical quantities, in this case some voltages, are equal to this SL1, which this multiplication by S denotes a differential operator times some current. Okay. And what is usually done is we make all the state variables voltages, because in our realization of the continuous time filters we will not have inductors. Okay. In place of every inductor, it will turn out we will have a capacitor. An inductor takes a voltage and integrates that to produce the current in the inductor. A capacitor takes a current and integrates that current to give a voltage across the capacitor. Okay. So, the function is basically either integration or differentiation, depending on the way you think about it, and it can be performed either with a capacitor or an inductor. We will do all our operations using a capacitor. Okay. So, all the state variables we have in terms of currents, that is inductor currents, we will normalize them by some resistance R to result in voltages. Okay. So, I will define I1R to be V1, so that even the first state variable is in terms of a voltage. If I do that, okay, these can be written as 2 Vi minus V1 minus V2 is equal to SL1 by R times V1, and similarly V1 minus V2 is SC2 times R times V2. Okay. And here it is the same, Vi minus V2 will be SL1 by R times V1, and this will be V1 minus V2 will be SC2R V2, and there Vi minus V1 minus V2 will be SL1 by R times V1, and V1 here will be SC2R times V2. Okay. So, here all the state variables are voltages, and this we can realize with a circuit that has only capacitors, where the state variables correspond to voltage across capacitors. Okay. So, it looks like we need to make certain voltages related to derivatives of other voltages. Okay. Now, these equations can be equivalently written as okay. So, these are written in a way that a certain state variable V 1 equals some combination of other voltages, which could be state variables or the input voltage, divided by S L 1 by R, that is these combination of voltages is integrated over time. Okay. Similarly, V 2 is given by this, which is V 1 minus V 2, and integrated over time gives you V 2 and so on. In all the cases it is like that. These equations are in a form which can be realized as integrators, which integrate a combination of voltages. Okay. So, it turns out that by implementing these equations we will get exactly the same function as in the original filter. Now, this is a very convenient form for us to implement as well, because we know that we can make integrators by using a voltage controlled current source, converting the voltage to a current, and then passing the current through a capacitor. So, that is how we can implement the integration, and the output voltage will be the voltage across the capacitor, and that is exactly what we want from these equations. Okay. Now, an alternative way of implementing integrator could be using an op amp in negative feedback. So, that is also possible. We will first look at how to implement these filters using voltage controlled current sources or transconductors and capacitors. Okay. So, how do we make an integrator? If we take a transconductor like this, whose value is Gm, and apply an input voltage Vi, at the output we will get a voltage Vi Gm by SC1. Okay. Now, if we want to integrate a linear combination of voltages, what we can do is have multiple voltages input like this. Okay. If we have that, then let us say we call this GM2, the output voltage will be Vi2 GM2 by SC1. So, this way we can implement a linear combination plus integration. Okay. So, the first way of implementing integration is through transconductors and capacitors, or what is known as GMC technique. Okay. And filters that use these are known as GMC filters. An alternative is to implement the integrator using an op amp. I will not go through the details here, but if we make a transimpedance amplifier, but replace the feedback impedance with a capacitor, we know that we can implement an integration. Okay. the output voltage here will be minus Vi by SCR, and I will show it along with a negative 1 gain. So, that at the output of that we will get Vi by SCR without a minus sign. Okay. So, this integrator is using op amp RC, and historically this kind of topology has been called active RC integrator. Okay. And filters that use these integrators are known as active RC filters. Now, what I will do is I will synthesize all the filters using either this GMC technique or the active RC, and I will keep this minus 1 here. So, that finally we get something without inversion, but this is at the block diagram level. Later we will see that we have to make fully differential implementations. So, this negative 1 block does not have to be explicitly implemented, it can be implemented simply by crossing wires. Okay. Also, for GMC filters I will not show the input with 2 terminals, I will simply show the transconductor. Let us say it is to be connected like this, Vp, I will show it as something with a single input and an output. It is assumed that this plus inside means that the current is being pushed out. Okay. And similarly, if I had to make something of this sort Vm, then I will show it again as a single input stuff, but with a minus inside the block. All these are just to reduce the clutter in the diagrams that I am going to draw. Okay. So, this means that a current GMVM is drawn into the transconductor. Okay. Again the implementation will be fully differential, and we will connect the transconductors appropriately, either positive or negative. Okay. So, now let us look at GMC implementation of these low pass filters. Okay. We will take the doubly terminated prototype. And we know that this circuit is described by these two equations. Okay. So, in our active counterpart we will have two capacitors C1 and C2 with voltages V1 and V2 across them, and V1 and V2 and the input Vi are related by these relationships. Okay. So, this part seems simpler, so we will implement that first. Okay. I will rewrite this as V1 minus V2 divided by R divided by SC2. Okay. This is equal to V2. Now, V2 looks like some current divided by S times C2, and this is what you would expect. If the current through the capacitor C2 is what is shown in the numerator, then the voltage across the capacitor C2 will be given by this equation. Okay. So, the current through the capacitor C2 must be equal to V1 minus V2 divided by R, or in terms of transconductances V1 times some Gm, where Gm is 1 over R, minus V2 times the same Gm. Okay. So, we have V1 here, we have V1 times plus Gm. So, I will do that, that gives me the first term, and I have to get minus V2 times Gm, and V2 is the voltage across itself. Okay. but we need it with a negative sign. So, we have that. Okay. And similarly, we can implement the other equation, the first one over here. The voltage across C1, the voltage V1 will be whatever current is flowing through the capacitor divided by C1, and that should be equal to 2 Vi minus V1 minus V2 divided by SL1 by R. Okay. So, what do we have? The current through the capacitor must be equal to okay, something like that, where we have some proportionality constant and we have 2 times the input voltage minus V1 minus V2. Okay. We assume that we have Vi here and we have to implement the factor of 2 in the circuit. Okay. And this quantity this has dimensions of transconductance, okay, and I will simply call that Gm again. Okay. So, what do we need to do? We need minus V1 and minus V2. To implement minus V1, I drive this node with a transconductance which is driven from V2. Okay. So, get minus V2. So, this will give me, if this has a value Gm times V2, and to get minus Gm times V1, we have yet another transconductor and something like that. Okay. And finally, to get 2 times Vi, we have to have plus 2 times Gm, okay, because the weight for this Vi is twice that of the others. So, we get that whole thing. Okay. This is Vi and that will be Vo, and this will implement exactly the same transfer function as between this Vi and Vo, which is the voltage across C2. Okay. So, by using transconductors and capacitors, we can emulate the equations of the second order filter and realize an active filter that has only active elements, which are transconductors and capacitors. Okay. We will quickly do this for the other two types, the singly terminated types, and get slightly different prototypes. In fact, that is probably what we will use more often, but this serves as a introduction to how to synthesize a GMC filter starting from doubly terminated LC ladder prototype. Okay. So, all I have to do is to get a singly terminated filter, I omit either the termination at the source side or at the output side. Okay. And Vi is what is applied here. And the state equations are given by these. As usual, in our active circuit, we only have capacitors C1 and C2. Okay. So, we can implement these two equations. So, V1 would be the current in the capacitor C1 divided by SC1, and that we would like to be equal to Vi minus V2 divided by SL1 by R. Okay. Then what do we do? We just find the current in the capacitor, and that will be equal to C1R by L1 times Vi minus V2. Okay. So, as usual has dimensions of conductance, and I will call that Gm. So, I drive this with Vi. so that VIGM flows out, and I have to drive another transconductor with V2, and this should have a negative weight, so that GM V2 flows that way. Okay. And similarly, to implement the second one, V2 will be IC2 divided by C2, and that is equal to V1 minus V2 IC2 by SC2, which is equal to V1 minus V2 divided by R by SC2. So, the current IC2 must be simply V1 minus V2 divided by R, okay, which is V1 minus V2 times this GM. So, I have V1 times GM by using a transconductor with a positive weight, and minus V2 times GM by using a transconductor with a negative weight. Okay. So, this implements the same second order equation, and the difference is that difference between that and the doubly terminated prototype is this particular transconductor. Okay. This is missing from the singly terminated prototype. But what is this element here? This is nothing but a negative transconductance connected in feedback, which is basically a conductance. Okay. So, we have the source side termination here, that is missing from the singly terminated prototype. So, in the active circuit also we have a conductance here. This conductance corresponds to the termination on the input side, and this conductance, which is again a negative GM in feedback, corresponds to termination on the output side. So, the termination on the input side is missing. So, the positive transconductor that we connect here, the positive conductance we connect here is missing. Okay. And similarly, you can work out the prototype for the other singly terminated case. I will just give the answer and you can verify if you got the same answer as I did. This is 2 GM, I will draw it slightly differently here. This is minus GM in feedback, which essentially forms a conductance GM. C2, and we have another termination, another conductance, transconductance corresponding to termination on the other side. This is GM, this is GM, and we also have negative GM going the other way around. Okay. And for the singly terminated filter with a termination on the output side, what we have is exactly this, okay, but without that one. And if we consider a singly terminated filter, on the input side, what we are missing is this particular termination. Okay. And you can see that all three topologies are very similar to each other. Compared to the doubly terminated one, the singly terminated ladders will be missing one or the other conductance. Okay. All of these are basically conductance GM okay, which corresponds to the termination resistance. Okay. In these two singly terminated cases, the transconductance value driven from the input voltage will be Gm. Okay. And in the doubly terminated case, it is 2 Gm, that is to compensate for the attenuation of the doubly terminated ladder. Okay. So, that the DC gain of all these filters equals 1. Now, if we know how to make a transconductor, we will know how to make this active filter. Okay. One of the interesting things is to see that we had an inductor in the passive prototype. Now, we do not have an inductor anymore, but we are realizing its operation using transconductors. So, let us see how that happens. Let us say we try to emulate an inductor by itself. Using not an inductor, but using capacitors. Okay. That means that I have to implement the voltage current equation of the inductor, but without using an inductor. How do I do that? I know that I1 is VA minus VB divided by SL1. Okay. So, the operation is that of an integration, which I know can be implemented using a capacitor as well. So, if I am given a capacitor C1, okay, and I have these two voltages VA and VB, I have to draw this much current I1 from VA and then push it into VB. Okay. I have VA and VB, and let us say this is Gm and Gm. The current flowing through the capacitor would be Gm times VA minus VB, okay, and the voltage across the capacitor would be Gm by SC1 times VA minus VB. Okay. Now, from VA I must draw a current that is proportional to this. From VB I should draw a current proportional to this, but with a negative polarity. So, if I do this, what happens is there is a current that is drawn, which is proportional to, which is equal to Gm square by SC1 VA minus VB. Okay. The value of this is also Gm, and similarly here I have to push the current out. So, I will use a transconductor with a positive weight, and the current being pushed out equals Gm square by SC1 VA minus VB. Okay. So, this entire circuit emulates this inductor, but without using an inductor. Okay. That is, it emulates the voltage current equations of the inductor. Okay. Is this fine? So, and this is a structure that you see repeatedly in active filters. Okay. So, this is known as a gyrator, and gyrator inverts the impedance. If you have a capacitor terminating a gyrator, from the other side it looks like an inductor and vice versa. In case of active filters, it is usually used to emulate inductors. Okay. And in our circuit also you can see structure that is similar to this, not the complete structure, but something similar to this one. Okay. So, if I highlight this part of it, okay, you see that I have exactly that over here. Okay. So, this is our GMC active filter, which is a second order filter, and we can realize higher order filters using a second order filter. Okay. Now, similarly, let us also do this with active RC circuits. Now, again I can do it for all three, but I will do it only for one of them, one of those three cases that I showed, that is a doubly terminated and singly terminated with either termination at the source side or the output side, and you can take the other two as an exercise and see what structures come out. Okay. So, as we said earlier, we have to have active RC circuits or op amp circuit which can perform the function of integration. Okay. An integrator using an op amp looks like this, and I will keep this -1 block so that I do not have the polarity reversal. If I apply Vi here, what I get here will be Vi divided by SCR, and here I will have minus Vi divided by SCR. Okay. So, let us implement one of the singly terminated prototypes, that is this particular one. Okay. And this we know has to implement the equations Vi minus I1R minus V2 divided by SL1 equals I1. Okay. And if we translate everything in terms of voltages, we will have Vi minus V1 minus V2 divided by SL1 by R will be equal to V1. And similarly, the other expression would be I1 divided by SC2 would be equal to V2, and by normalizing it with some resistance, we will get V1 divided by SC2R equal to V2. Okay. Now, this is the active RC integrator, and if I want to make a linear combination of voltages which has to be integrated, all I can do is add multiple input resistors here, and the output voltage will be we also get plus Vi2 by SCR2, and here minus Vi plus minus Vi2 by SCR2. Okay. So, this is exactly what we are going to have. So, we can make integrators with multiple inputs. So, in this first case, we need to have an integrator with 3 inputs. Okay. And this will be the output V1, and the 3 inputs would be Vi and minus V1 and minus V2. Okay. And the other integrator has just a single input, and that is equal to V1. Okay, I am running out of room here. This would be V2, and I have to connect minus V2 over there, which appears over here. So, I can do this. Okay. I have to connect minus V1 over there, which appears there. So, I can do that one. Okay. And this will be some C1 and that will be some C2. Okay. and if I redraw it more neatly, I will get topology, which is a classical active RC filter topology. Okay. So, the actual output must be inverted again to get rid of the polarity inversion. Okay. So, if I apply here, I will get V 1 and V 2, where V 1 is the scaled version of the inductor current and V 2 is the capacitor voltage in the prototype. Okay. So, this is a second order active RC filter. Okay. And this procedure again can be extended to higher orders by writing down the expressions appropriately. We will see an example of that later, and then translating the equations into active RC integrator implementation. Okay. So, now we know how to translate the passive LC ladder prototype into GMC and active C filter implementations. Like I mentioned earlier, all our implementations will be differential because of all the good things that differential operation offers, and the same holds for these GMC and active RC filters as well. I will quickly show how the differential implementation looks like, although in all the future discussions I will show the single ended counterpart, that is because otherwise the diagrams get very messy. And this also gets rid of the -1 blocks that we had in the active RC implementation, okay, that simply corresponds to switching the wires. So, this is what we had, and the fully differential implementation would be that each transconductor would be fully differential, and this negative sign means that if it is plus minus on this side, I reverse the polarity and connect it that way. Okay. That is all that is there to it. Similarly, this is positive, so I will have plus minus and drive C 1 here and C 2 over there. Okay. And here I will have plus minus, minus plus, and drive the capacitor. Okay. The voltage here will be V 2 and the voltage here will be V 1, the voltage here is V I. Okay. So, this is the fully differential GMC second order filter, and we will see more details of the implementation of such a filter. And similarly, with active RC, what we will have is, so instead of this we will have fully differential op amp, which we know how to build with common mode feedback and all of that stuff. and we will have 2 capacitors in feedback, one for each side. Okay. And we will have 2 input resistors. There will be a resistor across each of these, R and R. Okay. And this -1 simply corresponds to crossing the wires like that. Again we will have these capacitors. Okay. And to get the actual output voltage V 2, it will be simply to cross the wires, and V 2 will be like that, and V 1 will be of that side. Okay. And finally, I have to complete this feedback loop, which comes from minus V 2. Okay. And the same on the other side. So, this is a fully differential active RC filter, okay, of second order. And just as exercises, you can repeat this with the doubly terminated prototype and the other variety of the singly terminated prototype, and it will be interesting for you to compare those topologies with what I have shown here. Okay. And the input voltage is applied between these two, which is really the difference between VIP and VIM. So, the voltages that we see here V 1 and V 2 will be filtered versions of VIP and VIM. The desired output, the low pass filter output is V 2. Okay. So, what we have done in this lecture is to synthesize GMC and active RC prototypes starting from ladder prototypes, which we take as given. Okay. In the next lecture, what we will do is extend this to higher orders, or use the second order filters to make higher order filters, and discuss quickly some non ideal features of such filters and how to fix them. Okay. Thank you. I will see you in the next lecture.